All right, welcome back to the deep dive. So today we're cracking open a topic that I think a lot of developers have some pretty strong feelings about, whether they admit it or not.
Oh, absolutely. It's a language with a very interesting history.
Yeah, we are stripping away all the marketing fluff
Yeah.
and getting straight into the unvarnished truth about Dart. And honestly, looking at the history here, it is a bit of a roller coaster.
It really is. It's a language that has had to, reinvent itself more than once just to stay relevant.
I mean, if you just rewind the clock to, 2011, Dart was pitched with these absolutely massive ambitions. It wasn't just, hey, here's a new tool for your belt.
No, not at all. It was positioned to be the Java killer.
The Java killer.
And even bolder, the ultimate replacement for JavaScript in the browser.
Exactly. And if we're being, brutally honest right from the start, which is the whole point of this deep dive, it failed. It failed at those specific goals.
Completely.
It didn't kill Java. And JavaScript, well, I mean, JavaScript is still the air we breathe on the web. It didn't even put a dent in it back then. So, okay, if it failed at its origin story, what is it today? Because clearly it's not dead. In fact, looking at the numbers, it's arguably more relevant now than it's ever been.
Oh, it's far from dead. But the identity, it shifted completely. The reality today is that Dart is a client-optimized, multi-platform language. It's designed very, very specifically to fix the pain points of building user interfaces.
Right.
But we have to acknowledge the elephant in the room immediately. Its explosive growth is, maybe 90% tied to Flutter?
Yeah, you really can't talk about one without the other. In the job market, they feel essentially synonymous.
They are. I mean, if you aren't using Flutter, Dart's utility drops pretty significantly. You don't see a lot of people just, writing command line scripts in Dart for fun, though you can.
Right.
Although, and we'll get into this later, server-side Dart with things like Dart Frog is.
Yeah,
It's definitely maturing. But the reason Dart won, or at least found its footing after that really rocky start, it really comes down to how it handles compilation. This is the technical bedrock.
This is the part that really caught my eye in the research. The notes call it the compiler dual wield, which, I mean, it sounds like a video game perk or something.
It's a great way to put it.
But it seems to be the secret sauce here.
It really is. This is a major aha moment for understanding why the language feels the way it does to work with. Most languages, they pick a lane. JavaScript is JIT just in time.
Right. It compiles as it runs.
Exactly, which is why it's so flexible, but it can be, sluggish at startup. Then you have something like C++A, that's AOT ahead of time. It compiles to machine code before you ever run it. That's just raw speed.
And Dart just looked at both of those and said, why not both?
Precisely. Dart is one of the very, very few languages that does both effectively. During development, it uses JIT. This is what enables that sub-second stateful hot reload that Flutter developers are just obsessed with.
Oh, yeah. That's the killer feature for developer experience.
Totally. It compiles on the fly, patching the code into the running virtual machine so you can, tweak the UI and see it instantly without losing your state.
You change a color, hit save, and it's there. You don't lose where you are in the app navigation. You don't have to log in again. It's magical.
Exactly. And that magic is only possible because of JIT. It's analyzing the code, compiling the delta, and then injecting it into the running process. But you wouldn't want that JIT compiler running in production.
No, absolutely not. I imagine that's incredibly heavy.
It is. JIT is slow to start. It can cause stuttering while it warms up because it has to figure out how to optimize the code while the code is running.
Oh, I see.
And it's memory heavy. So for production, Dart switches gears entirely to AOT. It compiles everything down to native ARM or by64 machine code, and that's how you get that native performance on iOS and Android. It's really the best of both worlds, but it requires a very complex architecture to pull off.
That sets the stage perfectly. So we aren't just looking at syntax today. We have a serious roadmap ahead of us. We're going to go from some, basic syntax traps that trip everyone up all the way down into the deep internals, and I'm talking the garbage collector, memory spaces, and the uncomfortable truth about concurrency.
We are absolutely going to open the hood and see how the engine actually runs.
Let's start right there with that engine, the runtime reality. So the source material emphasizes pretty heavily that Dart is single-threaded. Now, coming from languages like Java or C++, where you're managing thread pools and synchronized blocks, that sounds, well, kind of limiting.
It sounds limiting if you try to program it like it's Java, and that's the friction point for so many senior engineers when they switch over. In Java or C++, you have shared memory multi-threading. You can have multiple threads accessing the same variables at the same time.
Which leads to all the classic nightmare scenarios, right? Locks, race conditions, deadlocks.
Exactly. You spend half your time managing the threads rather than actually writing the logic. Dart doesn't do that. Dart fundamentally avoids shared memory threading in its main execution context.
So how does it manage handling, say, a database call, a user tap, and an animation all at once? If it's one thread, shouldn't it just block?
It relies on something called the event loop.
Okay, let's unpack the event loop. I think people sort of nod their heads when they hear this term. Like, yeah, the loop. But how should we actually visualize it?
Okay, so the best way to visualize it is think of a single line at a ticket counter.
Right.
That's your one thread. There's only one clerk, one window open.
Just one clerk.
Just one clerk. The event loop is that clerk. It takes an event, maybe a user taps a button, a timer goes off, or a file finishes downloading. It processes that event, executes the code associated with it, and then it waits for the next one. It does exactly one thing at a time.
One thing at a time. So it's strictly sequential.
Strictly. I mean, it pulls from two queues, the microtask queue and the event queue. But at the end of the day, the clerk is handling one ticket, one person at a time.
So what happens if I decide to, say, parse a massive 50 millimeter JSON file right there in that line? I get to the counter and I just dump a suitcase of documents on the desk.
That's the trap. That is the classic blocking of the event loop. If you run a heavy synchronous calculation on the main thread, the ticket counter stops moving.
Okay.
The clerk is completely busy reading your giant JSON file. Meanwhile, the paint frame event arrives because the screen needs to update for an animation. The clerk ignores it. A user tap event arrives. The clerk ignores that too.
And that's when the user sees the app completely freeze.
Exactly. That's jank, dropped frames. The UI freezes solid because the single thread is busy chewing on that JSON file. The operating system is basically screaming at the app to update the frame, but the app is busy. It can't respond.
Now, here's a misconception I think a lot of us have, and the notes highlight this as a great lie. We see async and await in the code, and we immediately think, oh, this is running in the background.
That is the single most common misunderstanding in the entire Dart ecosystem.
Really?
Yes. Async and await do not create a new thread. They simply schedule work on the same event loop.
Wait, hold on. So if I await a heavy calculation, it's still blocking the UI.
If the calculation is CPU bound, yes. Async is designed for I/O operations, waiting for a server response, waiting for a file to read from disk, things where you're waiting on something else.
I see.
When you await an HTTP request, Dart registers a callback and just puts the current function aside, letting the event loop process other things while it waits for the network data to come back. It's like the clerk saying, go fill out this form and come back when you're done. I'll help the next person in line.
Okay, that makes sense.
But if you write a while loop that counts to 1 billion inside an async function and await it, you are just standing at the counter, counting to 1 billion out loud. You are blocking the entire line.
So async is for waiting, not for heavy lifting. It handles the gap in time. It doesn't add more processing power.
Perfectly put. It allows for concurrency doing multiple things over a period of time, but not parallelism doing multiple things at the exact same instant.
I want to circle back briefly to that JIT versus AOT distinction, because there's a really practical tip in the notes about performance testing that relates to this.
Yes. And this is a rule written in blood. Never, ever, ever measure performance in debug mode.
Why is that? I mean, I'm developing in debug mode. Shouldn't I know how it runs there?
Because debug mode uses JIT. It's optimizing for your development speed, fast compilation, hot reload, all that good stuff. It is not optimizing for execution speed. It inserts a lot of extra checks, assertions, and it doesn't optimize memory layout. It runs code much, much slower.
So if I'm testing animation and it stutters in debug mode, I shouldn't panic.
Don't panic. Test it in profile mode, or even better, release mode. Those modes use AOT. They are compiled to native machine code. If it stutters there, then you can panic.
And release mode does something called tree shaking, right?
Yeah.
Which is a great visual.
It is, yeah. It looks at your code and it literally shakes the dependency tree. Any code, any library, any function that isn't actually reachable from your main function gets completely deleted from the final binary. It's ruthless.
That's why Flutter apps can be relatively small, even if you include some massive library.
Exactly. If you import a massive utility library, but you only use one function from it, the compiler just throws the rest away. It also strips out the ability to generate code dynamically. There's no evil allowed in AOT mode. It's lean and mean.
Okay, let's move on to the type system. The notes call this safety and pitfalls. And Dart has something called sound null safety. Now we hear null safety in Kotlin, Swift, TypeScript. How is Dart's sound null safety different from, say, TypeScript's?
This is a really crucial distinction. In TypeScript, the types are often they're erased at runtime. It's a development time check for the most part. You can sometimes trick the compiler, or maybe data coming in from JavaScript might violate the types, and you get an error at runtime. In Dart, the system is sound.
What does sound actually mean in this context? Is it about reliability?
It's a mathematical guarantee. It means that if the compiler says a variable is a string and not a nullable string, then it is impossible for that variable to be null at runtime. The compiler is so confident in this that it actually optimizes away the null checks in the final binary.
Oh.
It knows they aren't needed.
So it's not just about stopping bugs before they happen, it's actually a performance optimization.
Yes, the CPU doesn't have to waste cycles checking, is this null, before it tries to read from it. It makes the compiled code smaller and faster.
That's really impressive. But, I mean, there's still ways to break things if you aren't careful. Let's talk about the variables. We've got var, dynamic, and object. I feel like var gets a bad rap sometimes from people coming from, like, a strict Java background.
Yeah, and it's mostly undeserved. Var is fine. Var just means compiler, you figure out the type. But once it figures it out, say it sees you assigned an integer to it, it locks it in. It's still strongly typed. You can't change it to a string later.
So it's just syntactic sugar, really. Saves you a bit of typing.
Exactly. It's just to save you from typing my string every time.
Okay. So then, dynamic.
Dynamic is the danger zone. I love how the notes describe it. The crutch that will break your legs.
Yikes. Okay, why is it so bad?
It essentially turns off the type checker for that variable. It disables all the safety systems. It says to the compiler, trust me, I know what I'm doing. But usually you don't.
Oh, right.
If you call a method on a dynamic variable that doesn't actually exist, the compiler won't warn you. It'll just crash at runtime with a no such method error.
So it basically turns Dart back into old school JavaScript for that one variable.
Yeah.
You lose all the benefits.
Precisely. And that defeats the whole purpose of using Dart. You should avoid dynamic at all costs unless you are dealing with really messy JSON from a legacy API or some old JavaScript interop where the shape of the object truly is unknown.
So if I really don't know the type, maybe I'm parsing some weird API response. What's the safe alternative? What should I use instead of dynamic?
You should use object. It's semantically similar. It can hold anything, but the difference is safety. Object says, I don't know the type, but I promise to check it before I use it. The compiler won't let you call a method on it until you do a type check, like if my var is string. It forces you to write safe code.
Got it. Okay, now what about the bang operator? The exclamation mark.
Mm-hmm.
I see this sprinkled all over junior developers' code.
Ah, the bang operator. It forces Dart to treat a nullable value as non-nullable. It's you telling the compiler, shut up, I know for a fact this isn't null. And the rule here is very, very simple. Do not use it unless you are 100% willing to accept a crash.
It's really that severe.
Yes. If you use the bang operator and the value turns out to be null, maybe a network request failed or a database field changed unexpectedly, it throws a runtime exception immediately. Boom, the app crashes.
Wow.
You're almost always better off using the double question mark operator for a default value or conditional access with the null.
So Dan's basically saying, I bet my job this isn't null.
Pretty much. And you will lose that bet eventually. The house always wins.
Okay, got it. One more keyword that seems tricky. Late.
Late is used for delayed initialization. It's a promise. You're saying, I can't set this variable right now in the constructor because I need some context first, but I promise I will set it before I try to read it.
But there's a risk.
A huge risk. If you break your promise and you access it before you've set it, you crash. But here's the kicker that most people don't know. Using late adds a small runtime check on every single access to that variable.
Wait, really? It's not just a compile time thing. The compiler doesn't figure it out.
No, the VM has to check, has this been initialized yet, every time you touch it. So it's actually slightly slower than a standard variable. Don't use it just out of laziness. Only use it when the logic of your class absolutely demands it.
That's a great tip. Okay, before we leave types, we have to touch on memory management, specifically with final versus const. I feel like people use these interchangeably, but they're not the same at all.
Not at all. They are very, very different under the hood. Final is a runtime constant. It means a variable is assigned once, but that assignment happens when the code runs. For example, final date equals datetime.now. You can't know the current time until the code is actually running.
Okay, so it's assigned once and then it's locked.
Exactly. And const.
Compile time.
Const is computed at compile time. It's frozen before the app even starts. The compiler calculates the value and bakes it directly into the binary. And this leads to something deeply important called canonicalization.
That's a $10 word. What does canonicalization actually do for me as a developer?
It means if you have two identical const objects anywhere in your code, Dart is smart enough to make them share the exact same address in memory.
So if I have a specific padding widget defined as const edge insets.all 8.0a in 100 different places in my app.
It is really just one single object in memory. One instance.
That's wild. That's a huge optimization.
And that's why using const constructors in Flutter is such a big deal. It significantly reduces garbage collection pressure. When Flutter rebuilds the UI, if it sees a const widget, it knows it hasn't changed. It doesn't need to rebuild it or allocate new memory for it. It's a massive performance win for almost zero effort. If the linter tells you to add const, just do it.
Okay, let's go deeper. We talked about the single thread and the event loop, but what if we actually need to do heavy work? What if we have to parse that 50 millibit JSON? We can't just block the UI. So the outline brings us to concurrency and the isolate truth.
Right. This brings us back to the great lie we mentioned earlier. Since async doesn't use a new thread, how do we get true parallelism? How do we actually run code on a different processor core? You need isolates.
So what exactly is an isolate?
Think of an isolate as a completely separate little Dart world. It has its own chunk of memory, its own event loop, and it runs on its own processor core if one is available. It is, as the name suggests, isolated.
And the key phrase here that stands out is shared nothing architecture.
Yes, this is radically different from threads in Java or C#. In those languages, threads share the same heap memory. They can look at and modify the same variables.
Right.
Isolates do not share memory at all. You cannot access a global variable in your main function from inside an isolate. They are complete strangers to each other.
That sounds safer, no locking issues or race conditions. But does it come with a cost?
It absolutely does, because they don't share memory. If you want to send data between them, say, sending that parsed JSON result back to the UI thread, that data has to be copied. It has to be serialized and then deserialized, marshalled.
So if I set a 10 millib data structure, I'm essentially duplicating that 10 millib in memory, at least for a moment.
You are. And that copying takes CPU time. It's not free. That's why for really large data, like raw image bytes, the notes recommend using transferable type data, or FFI pointers, which allow you to move the underlying memory ownership without actually copying all the bytes. But for standard Dart objects, there is a tax on passing data.
Now, isolates used to be really hard to set up, right? I remember seeing code with ports and messages and managing the life cycle.
Yeah.
There's a lot of boilerplate.
Oh, it was painful. You had to set up a receive port, a send port, listen to streams. It was a lot of code just to run a simple function in the background. But the ecosystem has evolved significantly. Now, for one-off tasks, we have isolate.run.
And that came in Dart 2.19.
I believe so, yes. And it abstracts all that complexity away.
So how easy is it now?
It's a one-liner. You just pass it a function, it spins up the isolate, does the work, returns the value as a future, and shuts the isolate down. It looks almost exactly like a normal asynchronous function call.
But isolate.run isn't for everything.
No, not at all. If you have a background worker that needs to stay alive, like an audio processor or a specialized heavy calculation engine that you need to query repeatedly, you don't want to use isolate.run. Because spinning up a new isolate takes time. It has to initialize a new Dart VM instance. If you do that every 100 milliseconds, you'll kill your performance. For those persistent workers, you still use the classic isolate.spawn.
Okay. The notes also mention isolate groups. What are those about?
This is a fairly recent optimization that really changed the game. It makes spawning new isolate something like 100 times faster.
Wow.
Basically, isolate groups allow the isolates to share the program heap, that's the compiled code itself, while keeping their object heaps completely separate.
So they share the blueprint, but not the house that's built from it.
That is a perfect analogy. Exactly. They don't have to reload and parse all the code libraries from scratch, but they still don't share your variables. It makes using workers much more viable for things like, say, processing a bunch of images in a gallery app.
That's a huge improvement. Okay, let's shift gears to the syntax itself. Dart has changed a lot since version 1 or 2. We're in the era of Dart 3+ Surge.
Oh yeah. If you're writing code that looks like Java 7, you are writing legacy Dart. You're fighting the language, not working with it.
And one of the big new features is records. Finally.
Records are fantastic. They are essentially tuples. Before records, if you wanted a function to return two things, say a latitude and longitude, you had to create a specific lat-long class or use a map or a generic list and lose all your type safety.
Right, it was always a clunky workaround.
Yeah. Now you can just return double, simple.
Are they performant?
Very. They are value types, they're immutable, and they're stack allocated, which means they are incredibly fast to create and destroy. It stops you from having to create a whole new class result just for a simple return value. It cleans up the code base.
And what about patterns?
Pattern matching is a real power tool. It allows you to validate the structure of data and extract the data you want simultaneously. Imagine parsing JSON. Instead of a chain of if JSON.contains key and then var add JSON tide, you can just match the shape of the JSON directly in one line. It makes data handling code significantly cleaner and safer.
And switch expressions.
Finally, the old switch statement was so clunky. You had case, then your code, then break, then case, break.
And if you forgot a break, you have those horrible fall-through bugs.
Exactly. Switch expressions are the modern, concise version. They return a value directly. It makes control flow so much more readable and less error-prone.
Now, here's a topic that I know causes a lot of headaches. Metaprogramming, specifically code generation.
Ah, yes. The build runner.
The bane of many developers' existence. I can hear the collective groan of listeners waiting for that command line to finish.
It's the old way. You write your code, you run Flutter build runner watch, you wait 10 seconds, or for big projects, minutes, and it generates those Dart files.
And they clutter up your file system, they confuse your IDE sometimes.
It's slow, it's clunky, but there's a new way coming. The notes talk about macros.
Macros, this sounds like a big deal.
It is the paradigm shift. Macros run as the compiler parses the code. They modify the code in memory.
No more Dart files.
No more Dart files. No more build runner. For example, instead of the old JSON serialization setup where you wait for the generator to run, you'll just use an annotation, like at JSON Codable, and the serialization logic happens instantly in memory during compilation.
Wow.
It's cleaner, it's faster, and it keeps the project folder tidy. It's a massive quality of life upgrade.
That is going to be amazing.
Yeah.
Let's touch on dependency management quickly. Semantic versioning or SEMVer. There's a trap here called the carrot trap.
Right. You see this in your pubspec.yaml all the time, 1.2.3. The carrot means I accept any version that is compatible with 1.2.3. So it allows 1.3.0, 1.4.0, and so on. It assumes that library authors follow semantic versioning perfectly and never introduce breaking changes and minor updates.
But we live in the real world and people make mistakes.
Exactly. Mistakes happen. A library author might accidentally push a breaking change in version 1.3.0. If you just have the carrot, your build might break suddenly one day, even though you didn't change a single line of your own code.
So how do we protect ourselves from that?
The lock file, .pubspec.lock. This file is generated by Dart. You absolutely must commit this file to your version control. It locks the exact versions of every single dependency that was installed. It ensures that what you build on your machine is exactly what the CI/CD server builds and exactly what your colleague builds. Never, ever ignore the lock file for an application.
Okay, let's zoom out a bit. Dart isn't just for mobile apps anymore. We've got advanced engineering topics here, backend, web, and FFI.
Right. Dart on the server is getting really interesting. You have options like Dart Frog, which is minimalist and great for microservices, and then ServerPod, which is more like Rails for Dart, very feature complete.
What's the reality of performance on the server, though? Is it competitive with something like Go or Node.js?
Well, it comes back to the event loop again. Dart has incredible I/O performance. It's great for waiting on databases or other HTTP requests. It has very low memory usage, too. But just like on mobile, if you have CPU-heavy tasks, you block the entire server.
So how do you handle that in a production environment? If I have an 8-core server and Dart is single-threaded, am I just wasting 7 cores?
Not if you architect it correctly. You have to use load balancers and containers. Since Dart is single-threaded, one instance of your app uses 1 core. So you need to spin up 8 instances of your Dart server, maybe via Docker or Kubernetes, to utilize all the cores. You don't manage threads inside the app. You manage instances outside the app.
That makes sense. Now, the web. The notes say Dart.html is dead. That sounds pretty drastic.
It is drastic, but it's necessary. If you are starting a new project, do not use Dart.html. That library was tied to the old way Dart interacted with the browser. The new standard is package.web.
And why the big change?
It uses something called static interop. It compiles cleanly to both JavaScript and, more importantly, WASM WebAssembly.
And what WASM-GC is the big game changer here.
Yay. Huge, a massive game changer. Historically, Dart had a lot of trouble with WebAssembly because WASM didn't have its own garbage collector. So Dart had to ship its own GC inside the WASM module, which was heavy and slow.
Okay.
Now, modern browsers support WASM GC garbage collection that's native to the browser's WASM engine.
But what does that mean for the user? Better performance.
It means Dart compiles to WebAssembly that is much smaller and runs much, much faster. It fixes the major issues Dart on the web used to have, slow load times and that jank feeling. It brings web performance much closer to native mobile performance. It's basically making Flutter Web a real contender for serious applications.
And speaking of native, let's talk FFI, Foreign Function Interface. This is for when Dart just isn't enough, right?
Right. Sometimes you need to talk to a native C library or use Rust for some high-performance number crunching. Dart's FFI is synchronous and incredibly fast. It calls C memory directly. It doesn't have the overhead that something like Java's JNI used to have.
And there's something called native assets, which sounds like the future of this.
It is. Historically, bundling C code with a Dart app was a complete nightmare. You had to configure Makefiles, CMake, Gradle, pod files for iOS. It was a mess. You had to basically be a build engineer to get it working reliably.
I've been there. It's not fun.
No. Native assets allow Dart to automatically handle the building and bundling of C or Rust code. You define it in your pub spec, and Dart handles the rest. It's going to make using high-performance native libraries completely seamless.
Okay, we have arrived at Section 6, the missing manual, memory internals. This is where we separate the casuals from the experts.
This is definitely deep internal territory. To really understand performance, we need to talk about the garbage collector and the generational hypothesis.
The generational hypothesis. That sounds philosophical.
It's actually a statistical observation about software. Most objects die young.
Okay. Meaning I create a variable, I use it for a split second, and then I'm done with it. It goes out of scope.
Exactly. In a UI framework like Flutter, just think about how many temporary objects are created during one single frame build. Rectangles, offsets, colors, temporary lists for mapping data. They are created, used to paint the screen, and then they're immediately discarded.
So how does Dart use that assumption to optimize its memory management?
It divides memory into two main spaces: the young space, which is also called the nursery, and the old space.
Let's start with the nursery, where objects are born.
New objects are born in the nursery, and allocation here is incredibly cheap. It's basically just bumping a pointer forward in a block of memory. It's super fast. When the nursery fills up, the GC runs what's called a scavenger.
The scavenger.
It's a very, very fast algorithm. It looks at the nursery and says, okay, which of these millions of objects are still alive? And because of the generational hypothesis, most of them are dead. So it just copies the few live objects to a safe spot and then wipes the rest of the space instantly.
So creating temporary objects in, say, a build method
Is almost free. The note says creating temporary lists and build methods is fine because they live and die in the nursery. The cleanup cost is proportional to the number of live objects, not the dead ones.
But what if they survive? What if an object doesn't die young?
If an object survives a few of these scavenge cycles in the nursery, it gets promoted. It moves to the old space, the retirement home.
And cleaning that up is harder, I'm guessing.
Much harder and much slower. The GC uses a mark sweep compact algorithm there. It's expensive. It has to walk through the entire memory graph of your application, and it causes what are known as stop-the-world pauses.
Stop the world sounds bad.
It's as bad as it sounds. It means your app literally stops running for a moment. Could be milliseconds to clean up memory. If that pause is longer than 16 milliseconds on a 60 Hz display, you drop a frame. You get jank.
So the optimization strategy as a developer is to try and keep things out of old space, unless they really truly need to be there for a long time.
Exactly. Avoid keeping long-lived references to large objects like in global variables or static caches so they don't get promoted to old space if you can help it. Or if they are in old space, make sure they stay there and don't get churned, causing constant cleanups.
The notes also mention weak references and finalizers. These sound like pretty specialized tools.
They are. You don't reach for them every day. A weak reference lets you hold onto an object but still allows the GC to kill it if nothing else is using it. It's great for implementing caches. And a finalizer is like a safe destructor. It runs a callback when an object is collected. This is crucial if your Dart object is holding onto a native C resource, like a database connection or a file handle. You use the finalizer to tell the C code to close the connection when the Dart object dies.
Okay, moving on to Section 7, Performance Tuning and Security. We have a jank checklist here.
This is a great list for anyone debugging a stuttering app. The first item is shader compilation.
This is that annoying stutter you see the very first time an animation runs, right?
Yes. The GPU has to compile the shader program the first time it sees it, which takes a moment. The fix for this is the Impeller engine, which is the new rendering engine for Flutter. It pre-compiles all the shaders when you build the app, so you don't get that first-run stutter anymore. It solves a problem that plagued Flutter for years.
Next on the checklist, GC thrashing.
The sawtooth pattern. If you open the DevTools memory view and the graph looks like a saw blade, up, down, very, very quickly. It means you are allocating a ton of objects in a tight loop, possibly a build method, forcing the GC to run constantly. You need to refactor to pull those allocations out of the loop.
And over-serialization.
Yeah, we touched on this with isolates. Sending large JSON blobs back and forth, it kills performance. If you are sending 50 millibeats of data to an isolate, maybe you need to reconsider your architecture or use FFI to pass parameters instead of data.
And intrinsic constraints.
Intrinsic height and intrinsic width. You see these widgets sometimes. For the most part, you should avoid them. They force the layout engine to do a speculative pass. It asks, how big would you be if I gave you infinite space? And then it does a real pass. It turns a linear layout process into an O and exponential mess. It's just expensive math. Only use them if you have absolutely no other choice.
Now, security. This one scared me a little. Shared preferences. We all use it.
Right, and the lie we tell ourselves is, I stored the auth token in shared preferences, so it's safe.
It's not.
No, not at all. On Android, shared preferences is just an XML file sitting in a public folder on the disk. On iOS, it's a PLIST file. If someone roots the phone or gets access to an unencrypted backup, they can just read it in plain text. It is not secure storage.
So what's the fix for that?
You have to use Flutter Secure Storage. It wraps the platform-specific secure hardware, the keychain on iOS and the key store on Android. It encrypts the data, so even if someone gets the file, they can't read it.
Good to know. Another security point. Memory scrubbing.
This is a tricky one. In managed languages like Dart, strings are immutable. So if you have a user's password in a string variable, you can't just overwrite it with zeros when you're done with it. It just sits in memory until the GC decides to clean it up.
So for high security apps, banking, medical, what's the mitigation?
For ultra-high security, you'd need to use FFI and C-style char arrays so you can manually manage the memory and wipe it clean yourself. But for most apps, just be aware that sensitive data can linger in memory dumps.
And finally, SSL pinning.
This is essential for preventing man-in-the-middle attacks. You hard-code the hash of your server's SSL certificate in your app. So if a proxy or a hacker tries to intercept the traffic with a different certificate, the app checks it, sees it doesn't match the hard-coded hash, and just refuses the connection. It makes reverse engineering your API much, much harder.
We're in the home stretch. Best practices and the senior mindset.
This is all about how you approach writing the code in the first place.
First up, linting. The nodes are very specific here.
Yes. You need to go into your analysis options.yaml file and enable strict casts.
No.
True.
Why is that one specifically so important?
It prevents silent, implicit conversions from dynamic. It stops code like int_text equals a JSON vol from compiling if the compiler doesn't know for sure that JSON vol is an int. It forces you to be explicit and write int_text JSON vol as int.
So it forces you to acknowledge the risk.
Exactly. It forces you to be explicit about your assumptions. It catches bugs before you even run the app. It turns potential runtime errors into compile time errors, which is what we always want.
And functional programming patterns.
Yeah, the result pattern.
Yeah.
Instead of throwing exceptions for expected things like user not found or wrong password, you should use a sealed class. Return either a success object with the data or a failure object with the error.
Because exceptions should be for.
Exceptional circumstances. The disk is full. The network cable was physically cut, not for controlling the flow of your application logic. Exceptions are expensive because they have to unwind the call stack, and there are like hidden GOTO statements. They break the flow of code unpredictably. Using a result type makes your error handling explicit and typed.
And finally, the senior mindset. The notes list a few key tenets here.
First one. Assume dynamic is a bug. Justify every single use of it. If you see it in a code review, ask why.
Treat it as guilty until proven innocent.
Exactly. Second, assume the network is slow and unreliable. Never code as if the backend is instant. Show loading states. Handle timeouts gracefully.
Understand the cost of your abstractions. A stream is heavier than a future. A future is heavier than a simple callback. Don't use a tank to go to the grocery store. Use the simplest tool that actually does the job.
And the last one?
Read the source code. It's the best documentation you will ever find. If you want to know how a container widget really works, Ctrl click into it in your IDE. See how the Google engineers wrote it. It demystifies the magic. You realize it's just Dart code, the same stuff you write every day.
That is a lot to take in. We've gone from Java killer all the way to WASM native. We've dissected the event loop and the garbage collector.
It's definitely been a journey.
So what's the final takeaway here, the provocative thought to leave with?
I think it's this. The transition to WASM native and macros suggests Dart is evolving faster than its reputation. If you are still writing legacy Dart, that old Java 7 style code, you are missing the entire point of the language. It's a highly specialized tool now, and if you respect its internal mechanics, the event loop, the memory model, it rewards you with incredible performance and developer experience. It's like a Ferrari, but you have to know how to drive it. You can't just floor it in first gear.
And for you, the listeners, here's the call to action. Don't just read about this. Go encounter these edge cases. Try to block the event loop on purpose so you know what it looks and feels like. And then go check your analysisoptions.yaml file right now.
Absolutely. Go turn on strict casts. Do it.
Thanks for diving deep with us into the internals of Dart. We'll see you on the next deep dive.